Auzu billahi minash shaitanir rajeem. Bismillahir rahmanir rahim. In this unit, we will discuss signal to noise ratio, noise factor, noise figure, and noise temperature. And all these are interrelated to the presence and impact of noise in wireless system. They also have different perspectives on noise characteristics, including its power, ratio to the desired signal, degradation in the SNR, and equivalent temperature. These concepts are very crucial in analyzing, designing, and optimizing communication systems to ensure reliable and highly quality signal transmission for wireless communication between transmitter and receiver. The signal to noise ratio is a measure of the ratio of the power of a desired signal to the power of the noise present in communication system. To quantify the quality and as well as the reliability of the signal in the presence of noise in channel. SNR is commonly expressed in decibels and it's calculated with a simple equation. SNR is equal to 10 log PS over PN. In this formula, PS represents the power of the signal and PN represents the power of the noise. SNR indicate how stronger the signal is compared to the noise. A higher SNR value indicate a strong signal, while a desirable signal with less interference from the noise, while a lower SNR value indicates a weaker signal and a less reliable signal that may be more susceptible to errors introduced by noise. SNR is a very critical parameter in a communication system and it directly affects the system performance, including the error rate and the achievable data rate. A higher SNR generally leads to a better communication performance, allowing for higher data rates and lower error rate. It is important to note that SNR can be influenced by various factors, including power level of signal and noise, the bandwidth of the system itself, and similarly the characteristic of the noise distribution in channel. In practice, engineers and researchers often strive to maximize the SNR by optimizing system design, employing the noise reduction technique, or increasing the system power while minimizing the noise power. SNR has been fundamental concept in communication theory and they play a very crucial role in the analysis, design, and optimization of the communication system across various domains, including wireless communication, fiber optics, and digital transformation. Noise factor is an indicator that quantifies a reduction in the signal to noise ratio within a device. The input signal to the noise ratio is divided by the output signal to noise ratio to obtain this ratio. Due to the inherent nature of the signal degradation, the noise factor is consistently lower as the signal to noise ratio at the output is always be lower than the signal to noise ratio at the input. Reducing noise factor lead to enhanced device performance and the simple equation for the noise factor is S input divided by N input and overall divided by the S output ratio with the N output. Where S input, signal level at input, N input, noise level at the input, S output, signal level at the output, and N out is the noise level at the output. Noise figure is the measure of the degradation of signal to noise ratio caused by the device or system. It is generally expressed in decibels and represents the ratio of signal to noise ratio at the input to the signal to noise ratio at the output of the device or the system. That lower noise figure indicate less noise added to the system or device, and resulting in a better SNR, and it is improved performance. The noise figure is often used to measure the noise performance of amplifier, receiver, and the component in the communication system. It characterizes the noise contribution of a device or system or a specific frequency range used for communication system. The noise figure can vary with the frequency due to the variation in the noise source, variation in the frequency response, and variation in the impedance matching. The noise figure is typically specified or measured at a specific frequency or frequencies range. For cascade system, the overall noise figure is determined by the adding the noise figure of individual component in decibel. The noise figure can be converted to the noise factor by taking the nuancing to the base 10 of a noise figure value we will discuss in the next slide. Can we strive to minimize the noise figure by selecting lower noise component, implying noise reduction technique, and optimizing system design to achieve better SNR and improve system performance? So noise figure is equal to 10 log F and NF is equal to 10 log SNR input divided by SNR output. And if we're taking the decibels, then NF is equal to SNR input decibel minus SNR output decibel. Where SNR input decibel and SNR output decibel are the unit of a decibel. The formula are commonly valid when the input termination is at a standard noise temperature approximately 200 Kelvin to 300 Kelvin. Although in practice, small difference in temperature do not significantly affect these values. Low noise amplifier is an inherent feature of a wireless transmitter. But in amplifier, the source output having a signal of power SI and noise power NI, both signal and noise get amplified. However, in addition to the amplified noise from the source, amplifier add additional noise to the output as denoted by NA. Therefore, the SNR at the amplifier side output is lower than the input level. In this figure, it clearly shows that uh, this NI is generated from the previous system given to the amplifier. Amplifier is amplified, and the output of the SNR is equal to S naught and N naught, which is equal to the S1 GG is the gain of amplifier, and NIG plus N. Here you will see that both uh, source SI and NI are gained due to amplifier, and N is further added. So this SNR and the output is equal to SIG divided by NIG plus NA. And after the simple multiplication, we can see that this noise factor can be equal to the 1 plus NA over NIG. The noise factor may be expressed as a function of additional output reference noise, power denoted by NA and the power G of the amplifier. The concept of noise factor or noise figure is not always the most convenient way of measuring noise. Another way to represent the noise by mean of equivalent noise temperature. The equivalent noise temperature, the simple noise temperature, is used to dealing with the ultra high frequency and microwave low noise antennas, receivers, and devices. The noise temperature of the system is defined as the temperature at which the noisy resistor will produce the same amount of noise power at the system output as that produced by the actual system. And noise temperature is one way to express the level here, and it can easily be calculated as Pn over B is equal to Kp, where Pn is the noise power in watt and B is the total bandwidth enhanced, and K is the Boltzmann constant, and T is the finally, we can conclude that SNR, noise factor, noise figure, and noise temperature, they are interrelated concepts and all are used to express the nature of the noise and to determine the ratio of signal to noise ratio with different aspects. Thank you.